So I'm happy to that Dr. Robin Selinger is here to talk about Kent State University programs and also about her research. And I'll let Dr. Kosminski introduce her.
Yeah, I'd like to thank Dr. Robin Selinger for coming to give a colloquium at Lewis today, well, on Zoom at Lewis today. Dr. Selinger holds bachelor's, master's, and PhD degrees from Harvard. After postdoctoral work at UCLA, University of Maryland, and NIST, she joined the physics faculty at Catholic University of America in 1995, and later moved to Kent State University's Advanced Materials and Liquid Crystal Institute in 2005. Her research has been funded by the NSF, the US Navy, and ACS-PRF. She is also strongly committed to STEM outreach and organizes a STEM internship program for high school students. She was a fellow of the American Physical Society and was elected general counsel on the American Physical Society Council of Representatives and is a member of the APS Board of Directors. Her recent research focuses on theory and simulation studies of soft matter. So let's welcome Dr. Selinger.
Hello, everybody. It's nice to have a virtual visit. I wish I were in Chicago. It would be nice to be able to travel. Hopefully, I will be able to travel again. I understand that in our audience today, do we have some students?
Yes, we have quite a few.
I can't see faces because cameras are off. So do we have mostly undergraduates or graduate students, Joe?
Looks like there's a good mix.
Okay, so what I wanted to let you know before I tell you about my work on liquid crystal polymers, I wanted to mention that there are opportunities for you to continue your education at Kent State University in Northeast Ohio. So we have PhD programs in physics, chemistry, material science, many other fields. I thought I would just mention those three. Our material science program is the one that I like the best, and it is really focused on soft matter and materials that are used to control light, electro-optics. We do not have strength at present in metallurgy and ceramics. We are really a soft matter-oriented material science program. And this Advanced Materials and Liquid Crystal Institute has been around over 50 years, and chances are the liquid crystal display on the device in your pocket was invented at Kent State. I just wanted to mention of the students that come through the PhD program in physics and in material science, I just made myself, see if I can get the page to change. There we go. I made myself a little cheat sheet of some students who've graduated from our program and where they've gone and what they've done. And I didn't put all their names here, but I thought I would just tell you about them. So the obvious thing to do with a PhD in physics or materials, we actually used to call our materials program chemical physics, is to go into academia. And here's a whole bunch of folks who went into academia. So for instance, Ivan Smolyuk is a professor at University of Colorado at Boulder, and he's really one of the leaders of the field of liquid crystals and soft matter experimental work. Shuang Zhou is at UMass Amherst. Viana Jimenez Pinto is a graduate of actually my group, and she is on the faculty at Lincoln University in Missouri, which is an HBCU. The vast majority of our students go into industrial R&D, and we have students at Apple. Let's see, this is Stephanie Tauschenoff, she's at Apple. Wilder Iglesias was at Raven Window, which I think has gone out of business, so he's working for another smart window R&D organization in Denver. Mitya Rezhnikov works for a Google subsidiary out in California. Sajida Afka is at Microsoft, and we have actually several of our alumni at Microsoft. On the category of people who are faculty, some of them rise into positions of leadership and authority. So Greg Crawford is president of Miami University of Ohio, and Joe Whitehead is vice president and provost at Bowling Green, also in Ohio. Some of our students end up at national laboratories. So let's see, Jake Fontana and Jacob Kolage are both at the Naval Research Lab in Washington, D.C. Valerie Finnemeyer is at Lincoln Lab, which is a federally supported lab affiliated with MIT, I guess. And this graduate, Sarah, where is she? She's at the the Air Force Research Lab at the Wright-Patterson Air Force Base here in Ohio. This young man, Andrew Konya, started a company. He did computational material science actually in his graduate work, and he started a company called Remesh that's raised over $20 million of entrepreneurial startup funding, and he's hiring. So if anybody's looking for a job in data science, he loves to hire physics majors. Now's a good time to look at Remesh. Some of our students are so good at data science that they go into quantitative finance. These two work in hedge funds. They're at a hedge fund in Chicago, actually, and they probably make more money than all the rest of us put together. And one of my graduates actually is vice president of PNC Bank in Pittsburgh. Unlike the United States, PNC has many vice presidents. It's not just one, but he is running their data science effort. And he also likes to hire physics majors to do interesting things in data science. So a PhD in physics or material science or chemistry, actually, from Kent State can take you all kinds of different places. Whether you see yourself joining the faculty, working at a place like Apple, designing, even though our students' degrees are in, physics or material science or chemical physics, their job title is often engineer. They are engineering displays. A whole bunch of our students work for Facebook. They design the hardware for the virtual reality headsets, the Oculus Rift, that whole class of materials. So these students know material science and they know optics. They've got clean room training. They know how to make prototypes and test and characterize a whole host of soft matter. Their backgrounds range from an undergraduate degree in physics, undergraduate degree in chemistry. Some of them even come from chemical engineering. We have a mix of students from all over the world. Let's see, so Shuang is from China, Vianney is from Venezuela, Stephanie is from Ohio, actually. Jake, I think I can't remember, California maybe. Valerie is from Pennsylvania. Let's see, Badel Mbanga, he is from Africa, from Cameroon. So people come from all over the world. Let's see, Jacob is American, but I think maybe he was born in Poland and is naturalized citizen. Mitya is from Ukraine. Sajida is from Iran. We have two from Turkey. This one is also from Ukraine, one from Brazil. So people come from all over the world. The faculty are also from all over the world. And it's just a wonderful, mutually supportive community. It's a wonderful place to be a graduate student, and our students go very interesting places. All right, so that's all I wanted to tell you about the graduate program. I'm happy to, if you are interested and you want us to contact you and tell you more about those graduate programs, I'm happy to tell you. But today I actually want to talk about science. So let me go back to Zoom and share screen, this one, and start that up. All right, so the first thing I have to ask you is, do you know what liquid crystals are? I don't know how to run a poll because I'm not the host of this Zoom, so I can't start a poll. But if you haven't heard of what liquid crystals are, I'm going to tell you at least a little bit about that. And today I'm going to tell you about not just liquid crystals, but liquid crystal polymers that are artificial muscles, and they can actuate like muscles and actually like make things move. So did anybody here ever wear a mood ring? Do you know what mood rings are? They are color changing liquid crystals. They're cholesteric and they change color with temperature. So liquid crystals can be used to control light. They can make fun toys that change color with temperature. Now we're going to talk about liquid crystals that can be used like artificial muscles, like in a robot. Okay, so liquid crystal phases. So the most important thing you need to know about liquid crystal molecules is that they are not spherical. They can be long and skinny like rods. They can be round and flat like plates, like pennies or pizzas. And because of their non-spherical shape, they can organize themselves in phases that are different from the usual crystal, liquid, gas phases that I learned about in elementary school, phases of matter. Okay, so the crystal state is characterized by a unit cell. The isotropic liquid state is characterized by disorder. right? It's a big jumble, like you threw a bunch of pencils in a box, okay? The in-between phases are called mesophases, where meso means like in between, middle. So if you cool the isotropic liquid crystal just a little bit, you get a pneumatic phase. The pneumatic phase has orientational order. In other words, the axis of the rods is roughly aligned and has long range order, but the positions do not fall in a unit cell. So it's like an aligned liquid. Okay, the name pneumatic comes, maybe you've heard of nematodes. Nematodes are long, skinny objects, right? So the Greek root pneuma relates to threads. And so when the pneumatic liquid crystal was first seen under a polarizing light microscope, the obvious visual feature of it was that it had many thread-like defects in it, where the orientational order is interrupted. And so it was called pneumatic because it was the thread-like phase. Okay, if you keep cooling, some rod-shaped molecules have another phase, a set of phases called Spectic Phases that are layered. And so it has translational order along one axis, okay, but then it's disordered in the plane. So it's like stacked two-dimensional fluids. And so if you do X-ray scattering experiments, for instance, you can see a clear signature of regular spacing along one axis, but it's liquid-like in the other two directions. Okay, so a smectic, where the average orientation is perpendicular to the layers, that's called a smectic A. But the materials can also tilt in the event that you know some of them have another phase, a tilted phase called a smectic C. And so the sequence of phases is different for every type of molecule. They're not always the same. If you look at flat disc-like molecules, they form discotic phases, which are stacked like Ritz crackers, right, in stacks, and those stacks can order. We can also have chiral liquid crystals where the molecule is handed, like a right hand and a left hand. It can be mirror images. If you have a system that just has one of the handednesses present, those materials tend to pack with a twist and make a twisted structure called a cholesteric phase. So the mesophases of liquid crystals are fascinating, and that is one of the things you learn about if you come to our PhD program in material science. Okay, liquid crystal elastomers are a pneumatic phase of a liquid crystal that's been polymerized. And here are some examples of how they move, and I want to explain what makes them move. So here's the simplest one. In this little picture on the left side, can you guys see my little arrow? I could switch to the red light again. Pointer options, laser pointer. Here we go. So if you look at this thing, the liquid crystal elastomer is the little skinny thin object in the middle, and it's the yellow part is tape, which is causing it to be attached to something. And then what's happening is current is running in this coil, and so when you run current in the coil, it heats it up and it shrinks. And when the current is turned off, it expands. And that's kind of a puzzle. When I was a little girl, my mother told me when you heat things up, they expand. And this one expands when it's cold and shrinks when it's hot. That's kind of a puzzle. The one on the right here, these two actually are both experiments that were made at the Naval Research Laboratory in Washington, D.C. The liquid crystal elastomer here is this little piece of tape, like a little film. It has a little weight hanging from it at the bottom, and it's attached at the top. And on the front and back, it has some conducting grease, which is used to create a capacitor. Like you apply a voltage across this little film, and when you turn the voltage positive, it twists in one direction, and you turn the voltage negative, and it twists in the other direction. The one in the middle, unfortunately, this one I don't have a movie for, but this is a little piece of polymer in the shape of a diving board. This experiment was done at Kent State by my colleague, Peter Palfi-Mahori, and he shines a little photo pulse on it on the top, and it pops up. It pops upward, right? So it also moves. So these are things that move in response to some kind of stimulus. So we call these polymers stimuli responsive because they respond to their environment in some interesting way. So the one on the left is responding to temperature. The one in the middle is responding to light, and the one on the right is responding to an applied electric field. Okay, so let's see if I can get this thing to change for me. There we go. So how does this happen? Okay, so we have a liquid crystal, but it's not just a liquid crystal, it's been polymerized. Okay, so let's look at sort of like the cartoon model. Why would the material respond to heat? Well, so here we have a polymer. This cartoon shows a polymer backbone, okay, with the liquid crystal dangling off of it. And when it's cold, those molecules are aligned in a pneumatic phase. And when it's hot, they go into an isotropic phase. And when they disorder their orientations, they drag the polymer chains with them, and they make the material shrink along the axis of pneumatic order. Okay, so that's an order-disorder driven strain. Temperature is not actually the best way to run a robot, because if it goes outside on a cold day, it might not work. It also takes a long time for heat to diffuse, but this is one way to make the material actuate. Okay, how about the one that actuates with light? Here's how that works. That material has been doped with a light-sensitive dye, an azobenzene derivative that has a photoisomerization. So in its relaxed state, which is the trans state, it's kind of rod-like and more or less fits into the liquid crystal. But when it absorbs a photon of a specific wavelength that it's sensitive to, it will undergo a transition, a photoisomerization, to an excited state, which is called the cis state, which is not rod-like at all. And it disrupts the pneumatic order and causes the material to shrink. So this is a light-driven response. This particular electric field response is driven by a tilting. So this is a Spectic phase, but it has a susceptibility to tilt under an electric field. That's called the electroclinic effect. And when you tilt it, just like library books on the shelf, when they tilt to one side, they get shorter in this direction, wider in that direction. So does the polymer, and that drives deformation. So you get a layer contraction in thickness and a width expansion. But because of the way it's glued and because of its shape and maybe a little bit of asymmetry between the way the front and the back of the material is responding, it also makes it twist. But in any case, that's why it moves. It's because the electric field induces tilt. So those are 3 ways to actuate our artificial muscle. Okay, let's see if I can try again. Okay, now the thing is, if the pneumatic director is uniform, then all you have is a material that just gets longer and shorter, like the picture I showed with the temperature, right? It's just simple. The pneumatic director is uniform. What if the pneumatic director goes around in a circle, for instance? So here's a case where the pneumatic director goes around in a circle. If you look at this through polarizers, you can see where the material is the pneumatic director is parallel to the polarizer or the analyzer. You would see dark, and otherwise you would see light. So you can see that there's really a bullseye picture here. When you heat this up, you get something that looks like a mountain or a volcano. Here's another one where the disc has been held onto a thin glass tube, just with a little bit of air suction, and then shine a heat lamp on it, and it goes from being a disc to looking like a flower, right? So it's turned into essentially a cone. So this shows us that if we have a complex director design, we can get a complex shape change that's not just something simple. Another option is if we have some twist that goes through the thickness of the film, then we can have a flat ribbon that either can curl into a hollow tube or into a twisted ribbon. And that happens also with temperature. And we can have a material, if you have the pneumatic director pointed, say, north-south on the top and east-west on the bottom, when you heat this material, it will shrink more on the bottom and shrink less on the top, and it makes the whole thing curve. So you would think if you design just the right director field, that is to say the orientation of the pneumatic order as a function of position on your sample, you could go from any shape to any shape. You would think you could make a little flat piece of plastic, the shape of a postage stamp, pop up into a bust of Einstein. Like you could just make anything if you knew where to put the pneumatic director field and if you had a way to enforce, to make that, to fabricate the sample that way. So let me show you some ways that can be done. It would be helpful if the computer would actually cooperate with me. Computer not being cooperative. Here we go. Let me just change the pointer option back to a regular. I don't know. There we go. So one way to do that is called blueprinting. And the idea of blueprinting is that you take 2 pieces of glass and put a local anchoring pattern on the glass. That is a surface treatment that makes the glass align the liquid crystal along a specific direction. One way we can do that is to coat the interior surfaces of two pieces of glass, one in front of the other, coat the inside with a material that can be oriented by polarized light. And then we can shine a thin beam of polarized, linear polarized light, like a raster across the cell, going left, right, right, left, right, left, right, left across the box, and put any pattern we want. In particular, we can put that bullseye pattern. Okay, then we have the cell all prepared. Then we fill the cell with liquid crystal, and we let the liquid crystal align with the pattern. And so since we have the same pattern on the front and the back, if the cell isn't too thick, the liquid crystal can align uniformly through the sample with those directors. Now, mixed with the liquid crystal, we include some monomers and some cross-linking agent. Okay, and then you shine light, UV light, through the glass and polymerize that thing, and you make a nice polymer that has the pneumatic director that you wrote on the glass inscribed in the material. And we call this blueprinting. And for a long time, like, I don't know, for 10 years or more, this was considered the best way to get some kind of imposed orientation. And the easiest thing was to put the same orientation through the thickness. You could also, if you want to, put different patterns on the front and the back. And then the liquid crystal might be kind of confused and has to figure out what to do. It will, and for instance, have a twist. Like I said, you can put a twist through the thickness, different kind of things. But you just do the surface treatments and then put the material in between the two treated surfaces and hope for the best. There's a newer way to do it, which is what they call 4D printing. That sounds even cooler than 3D printing, right? So 4D printing, the first paper came out in 2017, is the process of essentially, building an object with a 3D printer. And what makes it 4D is that it changes shape with time. And for instance, it might change shape on heating or when you shine light on it or some other way. And one way to do, so if this is a picture actually that came from the work by Tim White and Jennifer Lewis. If you remember this morning when you put toothpaste on your toothbrush, you're like extruding the toothpaste. Imagine that when you're extruding the toothpaste, if there's any elongated molecules in it, they will align with the extrusion direction. And if you can cross-link them quickly before they sort of drip off or flow very far, then you can trap that pneumatic order as written. And these materials can also undergo shape transformations. So when we blueprint thin films between two pieces of glass, we make a very thin piece of polymer that can go from a two-dimensional flat object to a three-dimensional object. It can curl, it can twist, it can bow, it can bend, it can curl, it can do all kinds of things, 2D to 3D. But once we're doing this printing jazz, we can print a three-dimensional object that transforms into another three-dimensional object. And what's really interesting is it can undergo instabilities where it basically kind of hops when it pops, just like those little toys you have where you deform them, put it on the table, wait a minute, and it will undeform itself and pop off the table. These things can pop as well. They can have very rapid shape transitions. There's another way, I don't think I have a slide for it, that's kind of interesting. You can use a magnetic field to orient the pneumatic liquid crystal. So if you, for instance, lay down thin layers of pneumatic liquid crystal and then apply a magnetic field that will orient just the free stuff that isn't cross-linked yet, and then just shine the light to selectively cross-link part of the sample, and then maybe move your magnet, align the free liquid crystal another way, and then again, boop, 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 you can just cross-link little voxels of the material, and you can do that layer by layer, as many cycles as you're willing to make on each layer. So in principle, we can control essentially a vector field that is a secret code written into the material as printed, as created, that encodes not only a final shape, but a whole trajectory of motion. I would call it a choreography of motion. So it's a programmable solid. It's not only stimuli responsive, like you shine light on and it moves or jumps or wiggles. You can actually program its entire motion by writing the molecular orientation vector field in the material. And I think that's just fascinating. So it's a programmable solid You cannot find these materials on the shelf at Best Buy quite yet, not in the toy department, and and not in the health and wellness, biological. It's not going to give you a massage. These things are all still applications that are in design. So that the goal is that these materials will be useful, for instance, for biomedical devices, that it's safe to integrate, to put next to tissue, either inside the body or on the outside of the body. So one of the things that fascinated me about this topic, this study of these, programmable responsive polymers, is that when I was a little girl, I was fascinated by television commercials for Legs pantyhose. The Legs pantyhose company came out with a new kind of pantyhose they called Sheer Energy, and they said, oh, these massage your legs all day. I thought that sounded pretty good. And I asked my mom for some. She's like, sweetheart, darling, you are too young to wear pantyhose. Well, a few years went by and I was a little older. She's like, okay, you're old enough to wear pantyhose now. You're a teenager. And I finally got a pair of Sheer Energy pantyhose. And you know what? They're elastic, but they don't massage your legs all day. They just sit there. They don't have a battery. They don't have any power. There's no massaging going on. But these liquid crystal elastomers, they have the ability to produce actuation. They need power, either from a change of temperature, an electric field, maybe shine a light on them, but you can actually get them to move. And so the possibility exists that you could have materials that would massage your legs all day, particularly if you have circulation problems and you need help. You know who else needs something to squeeze their legs? Fighter pilots. Is there anybody here who's interested in military service? If you are a fighter pilot and you are pulling a lot of G's as you accelerate upward, there is a risk that the blood in your body can pool in the lower half of your body, deprive your brain of oxygen, and you will black out and crash your plane. Okay, so pilots wear G suits that squeeze their legs. They also have some physiological maneuvers that they do to keep their blood from completely rushing towards their feet, to try to maintain consciousness under difficult situations. So, these materials might have potential to be leg squeezers as an alternative to just like inflating cuffs that go over the legs. Patients in the hospital recovering from surgery also wear inflatable cuffs on their legs to prevent blood from pooling in the legs and prevent blood clots from forming. So those are, an example of two places where a soft actuator might be useful. They could be useful for lots of other types of biomedical devices that apply mechanical stress inside the body without using a hard piece of plastic or metal or ceramic. They could be useful, for instance, to make a tactile display, whether for a blind user who needs a braille tactile display, or for any user who is, for instance, playing a video game and would like to have a tactile display. I know that there are already vests you can wear if you are gaming, and in the game you are struck by a projectile, you can feel a mechanical force on your vest to give you that sense of virtual reality of a tactile form rather than just a visual form or an auditory form. So soft actuators that move are, it's an emerging class of materials and it's looking for its future applications. Okay, I was going to say, if you have the material that's between the two pieces of glass, once you take it out, it still retains the order. This is the blueprinted material. There's another option though. You can just remove one piece of glass, keep the material on the other piece of glass, and then it's a deformable coating. So those are other types of things. The deformable coating, when it undergoes its transformation, will go from being flat to having some complex shape. It could change its coefficient of static friction. It could change its coefficient of kinetic friction, and you might be able to feel the bumps with your finger. There's all kinds of other things it might be able to do, like capturing nanoparticles and releasing them, capturing colloid particles and releasing them. So again, it's another way to control material properties by taking advantage of the stimuli responsive and programmable aspect of the material. Okay, let's see if I can get to the next slide. Okay, so this is the three-dimensional layer by layer system that I mentioned before. I think I will skip that for now since we already talked about it. I cannot get the computer to go to the next slide. How about if we do this? There we go. Okay, so for inducing motion with light. I was actually on Zoom this morning with Natalie Katsonis, and I should correct this slide. She's no longer at University of Twente. She just recently moved to the University of Groningen in the Netherlands. And this is the system that's driven by the trans-cis transition. When you shine light on the material, it changes its mechanical properties, it stretches, it shrinks, and you can see the little spring is moving. Okay, so what's interesting is that the trans to cis or cis to trans, you know, so so from trans to cis is photoactuation. You drive the photoisomerization, you've gone into an excited state. Okay, and then cis back to trans is a relaxation back to the initial ground state. And each of these transitions can be slow or fast, depending on which azo compound is used. And it can also depend on the light intensity and the wavelength. So in this video, you can see the light turns on and the material is just like slowly relaxing to its new state, and then you turn the light off and it relaxes to another state. In both cases, it takes a second or so for the system to finish relaxing. And those the speed of those transitions, this is now a chemistry issue. The details of the actual azobenzene derivative, which I've just drawn here as a cartoon, as a little stick, you know, or a little V, the details actually matter. So depending on the actual chemistry, you will get fast or slow transitions for one or the other. In some cases, the excited state could be stable for an hour or even for days, or it can just be, it can relax in just a minute. Okay, now to shape change, to model the shape change process. My background was in molecular simulation, and I would have liked to do a full molecular simulation of these studies, of these systems, and there are people doing molecular simulations. But I was really interested in asking questions, not about what's happening at the molecular scale and on, you know, nanosecond timescales. I was really interested in what happens at the laboratory scale and on timescales of seconds, if not minutes. And so that meant that instead of doing molecular simulation, I really needed to think like a mechanical engineer and describe my system not using a set of atoms or point masses, but through a finite element mesh. Finite element modeling, the finite element method, is simply a technique of solving differential equations by dividing the spatial domain of interest into little pieces, elements. In 2 dimensions, those might be triangles. In 3 dimensions, the simplest shape is a tetrahedron. And so I decided to try writing a model at the continuum level that would describe the shape change of the system. But I'm a physicist, so instead of just buying a finite element code like COMSOL, I decided to start from scratch and build one of my own. So the first thing we do is we take our material of interest, which might be a little strip of material, and we divide it in elements. And as I said, in 2D, that could be triangles, and in 3D, it's tetrahedra. So we represent the solid object as a set of little mesh points called nodes that are connected in these shapes, triangles or tetrahedra. And then that actually is an interesting story all by itself. So if you want to do triangles, equilateral triangles pack really nicely. In fact, if you want to make a very attractive floor in your bathroom and you want to, you know, during the pandemic, some of us are doing some home renovations, you could buy triangular tiles and you could lay them down. They make a beautiful lattice, you know, a triangular lattice. Some people call it a hexagonal lattice. And each triangle, you know, is surrounded by other triangles and it leaves no empty space. Well, you need a little empty space for grout. But anyway, basically the triangles pack perfectly in 2D. But if you tried that with pentagons, that would not work. Hexagons work, squares work. Pentagons do not equilateral pentagons do not tile the floor nicely. If you tried to do that, you would find big empty spaces where the pentagons don't quite fit. Okay, so when I wrote this code first using equilateral triangles, it was real easy. Just take a rectangular strip and divide it into equilateral triangles. I could do that. But then when I was ready to switch to 3D, I said, okay, let's use tetrahedra. Guess what? Equilateral tetrahedra don't pack in 3D. They just don't. Does anybody here play Dungeons and Dragons? You have tetrahedral dice? Get your tetrahedral dice if you own them and try to stack them. I mean, this is why Lego doesn't make shapes. They make, you know, squares and rectangles and various things. They don't make tetrahedral Legos because tetrahedra don't pack in 3D. They leave empty space in 3D, just like pentagons do in 2D. So I had to figure out how to mesh a 3-dimensional structure in non-equilibrium tetrahedra. Okay, so there's meshing programs. One way to do it is to cut your system up in cubes. That's super easy. And then you can slice cubes in tetrahedra in different ways. But anyway, so we're describing our system by a set of, this is a continuum level model. And so, for instance, in each element, we can define a mechanical strain that it tells me how much it's been stretched. So if I know the positions of the tetrahedron in the unstretched state, and then I deform it and I've moved those particles, I can calculate the strain from the after to the before, right? The difference, those displacements. And epsilon ij is a strain tensor that defines the amount the material's been stretched. Okay, it's a tensor. That's why you see all this IJKL stuff. And just the same way we write a potential energy for stretching a piece of elastic or a Hooke's law spring in freshman physics, we write 1/2 kx squared, where k is a Hooke's law constant and x is a displacement. The analog for nonlinear elasticity is that we can write a potential energy density that goes like 1/2 times, instead of just a Hooke's law constant, we actually have a tensor, because the material will respond differently if you stretch it versus if you shear it, like different types of deformation. So something like 1/2 kx squared, but in this case, it's 1/2 Cijkl I epsilon ij epsilon kl. So it's like a tensor product, but it's basically like 1/2 kx squared. That's elasticity. That's the energy to stretch the material. Okay, this is a Hamiltonian. It has not only a potential energy, it also has a kinetic energy. So if I just imagine that in my mesh, I'm going to put all the mass on the corners of the mesh, what we call the nodes. And so each element has a certain amount of volume multiplied by the density. That's how much mass is in the element. And I'll just divide it evenly among the 4 nodes in each element. So each element gets a little mass. I mean, each little node gets a mass from each element of which it's a member. And if it has a velocity v, then I can write 1/2 mv squared, and that's the kinetic energy of that node. So I have potential and I have kinetic. And if I just have those two, I'm describing an elastic solid. By the way, there's more than one way to write the energy. This is just one way to write the potential energy. There's actually a lot of different ways to write the potential energy for an elastic solid that would be relevant for different types of solids. The same way in molecular modeling, we would use different molecular potentials to describe the energy of interaction between different species of atoms or molecules that would be appropriate for, copper or silicon or whatever material. There are different models of elasticity that would be more relevant for different materials. What makes liquid crystal elastomers interesting is that there's a coupling between strain and pneumatic order. So when a liquid crystal in the pneumatic phase is being heated, the quality of its orientational order is described by something called the scalar order parameter. And it's a first order phase transition. It drops to 0 at the transition from the pneumatic to the isotropic phase. And so how much that scalar order parameter has dropped controls how much the material stretches. That's the coupling between the polymer backbone and the pneumatic, the molecules that are the mesogens, these molecules that form the mesophase that are attached to that polymer backbone. And so there's a coupling that multiplies the strain times the change of the scalar order parameter. And it's because this term changes that makes the whole object move when it changes temperature. Okay, so enough chit chat. Let's actually look at those simulations. So here's a simulation of a flexible disk. So imagine you were on the International Space Station and you had a little rubber disk and you give it a little flex and you let go and let it float in front of you, you would see it oscillate. And here you can see the color represents the local potential energy. So this is without any liquid crystallinity. This is just a piece of floppy rubber. We did the same type of test run with a very soft solid. We call this dancing tofu. Okay, so basically from the point of view of, if you've had advanced mechanics, once you have a Hamiltonian, you can write equations of motion, but they really come down to F equals ma. So, right, so we're using our simple model to calculate the force on each node, and we're integrating the equation of motion forward in time. And here again, color is just showing the local potential energy density. So where you see red, that's where the material is really compressed or stretched. And if you were on the space shuttle, on the International Space Station, we don't have a space shuttle anymore, then you could do this experiment on the right with a piece of Jell-O or a piece of tofu. but you would have to get a special material that actually shows you its potential energy, you know, how much stretched or compressed it is to see the colors. I understand that Python programming is popular with physics majors in your program. So I hope you are might be interested to learn. Do you know anything about GPU-enabled computing? That means we hijack the NVIDIA graphics card in the computer that was originally designed to decide what goes on each color pixel on the screen. So it was designed to do parallel computing because it had to figure out what goes on each pixel at every moment in time. Okay, well, some brilliant person figured out how to hijack that parallel computing capability to do really fast math. So essentially, one little computer can be a virtual parallel supercomputer. And one of my brilliant students took our nonlinear 3D elastodynamics algorithm and ported it into the GPU-enabled computer and made it run in CUDA. So essentially, we're calculating what's happening on every node at the same time. And this algorithm is completely parallelizable, just as molecular dynamics is. And it runs almost, we can run the simulation almost as fast as the material can actually deform. So I would say we are close to being able to use the algorithm for video gaming, but we're not maybe quite there yet. I guess if we used a smaller mesh, we could use this for video gaming. I was at a social event and met one of our graduates from the physics program. Actually, he never finished his PhD. He went to work in a video gaming company instead of finishing his PhD. And he told me, oh, we never do finite element simulations in the video game. They're too compute intensive. I'm like, nuh-uh, we got a fast algorithm. You should be using this one. Okay, so so here's another piece of dancing tofu. So when the tofu is bouncing around, we could ask, what is, if we don't put any dissipative forces in the model, no internal viscosity, then the sum of kinetic and potential energy should be conserved. And so here's a graph that we made when we were testing the algorithm. So here, red is kinetic energy, blue is potential energy. We started the material with some velocity. And as you can see, they both jump up and down. And this black line, that is not an axis. That is a rock solid sum of kinetic and potential energy. And this was about 50,000 nodes and 30,000 elements. So if we want the material to relax to mechanical equilibrium, then we have to put some dissipation in. So it'll stop oscillating and slow down and stop. I mean, so the real equipment, I mean, the real sample that we're studying might be well over damped. But this is, this is like zero damped. If we put zero damping, we can see the algorithm is good enough to give us complete conservation of kinetic and potential energy to very high precision, which is cool. Okay, latest stats on simulation speed. If you care about simulation speed, we can run a system with 1 million elements, single GPU equipped with 28 cores, and we can get 1,000 time steps per minute. If your time step is less than 1,000th of a second, we can model the motion in the same amount of time it takes for the motion to happen. Our computer facility is the Owens cluster at the Ohio Supercomputer Center in Columbus. Luckily, through the magic of the internet, we don't have to actually physically go there, but they have plenty of GPU-equipped nodes. One of my students, maybe two of my students, have computers on their desk that have an NVIDIA graphics card in it, but the ones at the OSC are better than the ones we own. So we like to test our codes there and benchmark them. And I'd also like to show you the mesh that we use can either be an ordered mesh. So here we have cubes that have all been sliced, or it can be a disordered mesh. And we've tested both of them. We use different ones in different cases, but this kind of mesh in principle we could do by hand. The disordered mesh we typically use, even though I'm a real DIY person in general, I don't insist on doing everything myself. We did use some meshing software developed by other people that is optimized in various ways that maybe would be better than what we could do brute force on our own. But what you can see is that this particular one, it's a few elements thick. But if we have very, very thin films, we have to mesh down pretty small. And then we have a very fine mesh, and the code can run kind of slow. So we have to be careful about the aspect ratio of the things we're trying to model. Okay, computer's still not working. Let's try again. Next, there we go. So if we have a topological defect in a freestanding thin film, Okay, so here's that little disc. And let's see, is this video running? It is. So as it turns into a mountain, before it goes, it doesn't go directly from a disc to a cone. It goes through a hat shape first with the brim. Let's see if I can get this video to run again. There we go. So you can see because it has a finite thickness, as it's deforming, it goes first to a hat with the brim, and then the brim flips down, and the material eventually ends up as a cone shape. So this is what we can learn from the finite element simulation that we couldn't learn, for instance, by just doing analytical calculations where we often neglect the bending energy of the thin film. If you treat it as infinitely thin, you will miss the pop through hysteresis. Okay, now what if we put more complicated shapes in? So one of our favorite experimenters, Tim White, who used to be at the Air Force Lab and is now at University of Colorado, put in complicated looking defects in the model. So if you take a pencil and point your pencil, I can't do that, I think, with any of my pointers, but you can see here as you go around the center of the circle, the director rotates 4 times. So you can see this complicated structure. And when you heat something like that, there's nothing that breaks the symmetry between the front and the back. And so in principle, each little section of it can pop forward or pop backwards, and you get a rather disordered looking structure. The experiments were done with the heat always coming from one side. So we tried to model that, and we modeled the system so that if we always heat from the top, so there's the thermal gradient, the top is hotter than the bottom, the scalar order parameter is lower on the top and higher on the bottom, then lo and behold, the system always pops one way, and you get this very attractive thing that looks like a candy dish. Or let's see, there's an old-fashioned device you used to make orange juice where you cut your orange in half and rotate it on the juicer, and the little ribs of the juicer help get the juice out. Or I think I have a device that holds deviled eggs that looks kind of like this. So let's see if I can get that video to play again. So here's a disordered one that looks kind of nubbly, with parts popping up and parts popping down. And then the other one will go any minute now. There we go. And you can see it always pops the same way. Oh, my time is almost up. So let me see what else I can tell you. I'm going to cut forward. Well, here's one of those 3D samples popping through also. Let me tell you real quickly about the story of the robot that is powered by light and walks. This is an experiment that was done by Helen Jelibar, a graduate student of Dick Brouwer at the Technical University Eindhoven in the Netherlands. So here we have a very thin piece of polymer attached on 2 sides with some UV light showing on it from the side. And if I can get that video to play, please play video. No video play. Here we go. So when the light shines, the material dances. Okay, and this sample and this sample are the same except one turns upside down, and the one that's right side up dances fast with waves moving to the right, and the one that's upside down dances slow with waves moving to the left. So Dick Brouwer called me up and said, we have this really cool experiment, but we really don't understand how it works. Can you use your model to figure it out? And I said, would I? What a great idea. So there's the fast one, and the other one was slow. Okay, so what's going on here is here's Helen Jelibar and Dick Brouwer. This material has a pneumatic director parallel on the top and perpendicular on the bottom. And this material is doped with that photo actuating dye. Both transitions from trans to cis and cis to trans take about a second, maybe just a little less than a second. And it's when the planar side is on top, we got fast waves dancing to the right. And when the homeotropic side, that is to say the perpendicular side was on top, we got the slow waves moving to the left. Okay, so the clues we had about how this photo actuated system works is that it only oscillates if you have that splay geometry where you have parallel on one side and perpendicular on the other. Not if they're both perpendicular, not if they're both parallel. And it only occurs if there's light coming at an angle from one side. So self-shadowing plays some kind of role. Okay, so the changes in the pneumatic order are not uniform in the sample. The parts that are getting light are shrinking, the parts that are not getting light are relaxing, and that process is what's driving the oscillation. And so we had to actually figure out how to do ray tracing to figure out what part of the sample is in light and what part of the sample is in darkness. Our model is kind of simplified chemically. Instead of really thinking in a detailed way about the chemical kinetics of the trans to cis and cis to trans, we just said, let's just say there's an upper limit of pneumatic order and a lower limit of pneumatic order. And when you shine light, material goes all the way into the disordered state. And it takes about a second. And if you take away the light, it relaxes back in about a second. So it just, as the material gets light or doesn't get light. Okay, so this simulation was done by my student, Michael Varga. And you can see the light is coming from in front of the screen and it's making this object have the moving waves. Okay, and it turns out this model can completely reproduce the behavior of this peculiar experiment. So for instance, if the planar side is up, you can see waves moving to the right. So if the light is coming from the left side, you see waves moving to the right. And then if the light is coming from the other side, homeotropic side up, whoops, this one, then the material dances much more slowly and the waves move toward the light instead of away from the light. And so the mechanism is entirely driven by self-shadowing. That's what's making it oscillate. To do something interesting with this material, our colleagues at Eindhoven, instead of gluing the material to the table or clamping it down, they attached it to a very lightweight rectangular frame. And then when they shine light on it, it crawls. And so if the planar side is up, it crawls away from the light. So again, the light is on the left side in this image. And then if the other side is up, it crawls toward the light, but more slowly. Kind of in slow motion there. So there is no battery attached to this robot. It's entirely responding to light. And maybe it's absorbing heat from the ambient temperature of the room it's in. Okay, but this means we could create a device that sits in the desert and just crawls towards the sun or away from the sun, depending, which side of it is up. So it's a really interesting and intriguing light-driven device. And the code word for this project is walking on sunshine. Okay, so they didn't drive it with sunshine. They drove it with intense UV light, which I don't recommend because it could, damage your eyes. So this is another homeotropic side up. And they were trying to, different ways to get it to carry stuff, get it to shake off sand that's sitting on top of it, all kinds of things. So this work was published in 2017 in a paper in Nature. The first author is Anne-Helene Gelabar, and some of the movies are attached, both the movies of our simulation and, more exciting, the movies of the actual robot doing all kinds of cool things, carrying a little piece of cargo, shaking off the sand, all those fun things. Okay, since it's 4 o'clock, I think I'm going to skip some of the other things. Maybe I just want to show you. You guys know how an octopus picks things up? An octopus has an array of suckers. So here on the bottom right, you can see these little suckers. Those are just part of the robot's anatomy. I'm not the robot, the octopus's anatomy. And the octopus can just grab something nearby in the water, something that's not porous. You can't pick up a sponge with a suction cup, but you can pick up a glass cube or a fish, more to the point, which, the octopus is hungry. Okay, so my brilliant student, Yusuf Golestani, figured out a way to design a vector field, not for a freestanding thing like an octopus arm, but just for a surface. So you have a thin film attached, liquid crystal elastomer attached to a surface, and it starts out flat, and when you heat it up, it gets this shape. And so it could be used to pick things up. So we're looking at this as a model to create biomimetic octopus suckers. And after we get it working on a flat surface, then I think we would try to put it on a movable surface. And we would also create programmable elements that would allow the arm to go up and down and then grab onto things. So it's a tantalizing idea of a fun application for this kind of stimuli responsive programmable solid. If we could get it to actuate with electric field rather than with temperature, that would probably be good from the point of view of making the robot work, whether the water is warm or cold, whether the air is warm or cold. So this equation is actually the shape, it's the angle of the pneumatic director as a function of distance from the center of this object. And these are other parameters that describe the width of the core of the defect, and the spacing, r is the radius of them. So that's kind of fun. Anything else? This just shows you the finite element mesh that Yusuf used when he modeled the surface. So yeah, we're hoping to make a biomimetic octopus arm. Let's see, anything else I want to show you just for fun? We can use our finite element approach also to model colloidal solids that are kind of squishy. So when you sit on a beanbag chair, the little beanbag beans compress, okay? And they don't stay round, they change their shape. And modeling that is kind of complicated, and they undergo some shape transformations. This is actually a model of swelling of deformable colloids. So Manuel Valera at Slippery Rock and Craig Maloney at Northeastern we're talking about doing, this was actually a model by one of Craig Maloney's. Actually, no, I think Manuel Valera did the simulation. But anyway, so we're thinking about ways to use that. And, they don't have to be round, they can be triangles. Let's see if there's anything else I can show you. We're also working on active matter. So active matter is like self-propelled particles. And as you can see, the flexibility, the bending modulus of these driven particles completely changes their behavior. Active matter is one of the most popular fields right now in computational physics, and especially during this pandemic time when people have been stuck at home, modeling is a lot easier to do than laboratory experiments, although there are also some beautiful laboratory experiments in active matter. And there are several researchers at Kent State doing experiments on active matter, and they can do experiments with bacteria swimming in a liquid crystal, or it could be microtubules driven by molecular motors, all kinds of fun things. So we're doing some work on some computational work on active matter. I think I will skip all of those things. Here's more. We can put the active matter on curved surfaces. So I think I will just say here are some of my collaborators. And we are always looking for new collaborators. We're always looking for students to join our PhD program. Sometimes there are postdoctoral opportunities. So I'm happy to talk to you about all of those things. And I'll just mention that the hardest problem to solve, we know if we have a material and we know how the pneumatic director is organized and we know what light is shining on it or what temperature it is or what electric field is applied, we can calculate the forward problem. How does it move? What happens next? What we don't know how to solve is the inverse problem, which is to say I have my little postage stamp of material. I would like it to pop up into a bust of Einstein. How do I write the pneumatic director to make that happen? That's the inverse problem. And we are working on that. And we're going to be trying to address it actually with machine learning by giving a learning algorithm many examples of the forward problem from which it can, on its own, by magic, figure out the inverse problem. Because a lot of people have been working on the inverse problem. Ain't nobody solved it yet. So we're going to hope to make some progress on that in coming months. Thank you very much for your attention. I feel like I've been talking to a blank wall because I haven't been able to see your faces. But please feel free to turn on your camera, ask me questions. Joe or Carrie, I don't know how you like to handle those things.
Yeah, well, thank you, Dr. Selinger.
Should I stop sharing so I can actually see faces?
Yeah, so so we have time for some questions. Just go ahead and raise your hand and I'll call on you to ask your question.
The silence is deafening.
All right.
I can kick one off. This is Jason Kelleher, chair of the chemistry department. How are you, Robin?
Hi, Jason. Nice to meet you.
Nice to meet you as well. So this was quite an interesting talk, and it really highlights the value of the energy material interface that's going to drive things, right? My big question is, how touchy in those models is how touchy is the simulation? Because you are looking on the macroscopic scale, it seems like in a lot of these cases, to the rate of switching, right? Because if you think about the dependency or the time dependency of the photon absorption and then the energy transfer, a lot of these simulations take into account the macro properties, but is there any simulations that will take in the time dependency of switching? I guess that's my question.
Yeah, our models were at such a coarse grain scale that we just treated that as essentially a relaxation time for the pneumatic director as a function of illumination time.
Okay.
But yes, there is. So David Statman, and I'm trying to think, he was at Allegheny College. I don't know if he's still there. I haven't seen him in a while. He might have retired by now. He was doing some work on kinetics of the transist system. Natalie Katsonis, that I was just speaking about, has also done, I think, some very careful experiments on how to make that fast or slow. So the chemical details of the azobenzene derivative make a huge difference. And I would imagine also that Dick Brower's group in Eindhoven has a whole library of different dopants that they can use that are fast or slow. And I'm trying to think who else, maybe Helena Godinho in Lisbon, or Eugene Terentiev in England. My colleague Peter Palfi-Mahori at Kent State at some point got a grant from NSF to create essentially a giant recipe book for liquid crystal elastomers, where he got every researcher that had a formulation and got them all to essentially, write it all down. And actually for a while, he had like enough grant funding to provide samples to anybody who wanted them. But I think that grant is finished. I don't know if he's doing that anymore, but certainly the collected recipe book, sort of like The Joy of Cooking, but for liquid crystal elastomers, like a comprehensive collection of all recipes. And it's not just the chemical constituents, it's also the processing. Because to get the material, the very first alignment was achieved by partially cross-linking a thin film, and then they literally hung paper clips from it. Like, they always seem to use office supplies, like paper clips, little binder clips, hang it up and then shine light on it and let it finish cross-linking.
Low cost of ownership research, right? I mean, at that point, when you're using the office supplies, right? So
one nice thing about liquid crystal research in general is that it's tabletop. You don't need a giant group and you don't need a giant facility. A lot of stuff can be done small.
Outstanding. Thank you very much.
Thank you. Any students have questions? Or faculty, either way? Any students want to talk about grad school applications? I understand there are master's students and undergraduates at Lewis. Anybody interested in applying to, well, also we have master's programs at Kent State, but if you're finishing a bachelor's degree, you can apply directly into the PhD program. Students often receive a master's on the way to the PhD, but you don't have to apply just for the master's program first. Students who are already in a master's program can transfer some of their relevant credits, whether they're coming into physics, chemistry, or the material science program. Chances are some of your graduate credits will transfer and shorten your time to degree. So students who come in with a bachelor's degree typically need 4 semesters to complete their coursework. And during those first 2 years where they're taking courses, they tend to get their financial support from a teaching assistantship. So you would be supervising undergraduates in the lab or leading recitation sections. After the first 2 years in material science, all the students are supported on research assistantships, pretty much 100%. There's a rare exception with a student that really wants more teaching experience, but for the most part, they're all supported on RA research assistantships. In physics and chemistry, it's more common for older students. Students beyond the first 2 years can still be supported on teaching assistantships, which is, a break for the faculty in terms of their grant dollars. Life in Northeast Ohio is actually pretty sweet. Kent is a cozy college town within an easy commute distance of larger cities, Cleveland and Akron, that have some of the big city conveniences we need, like airports and concert halls. But Kent has a low cost of living, low crime rate. It's got a vibrant downtown that the undergraduates love, although I have to say in the age of COVID, things are awfully quiet there, but they're opening up. The late night curfew was recently ended because the number of COVID cases in Ohio has dropped significantly. And so this is actually a place where students can live quite comfortably because rents are low compared to a place like Chicago. Cost of living very modest. And students can actually live within a walk of campus. Or if they want to live further, there's parking available on campus, there's public transportation, there's a bus system, people bike when the weather is nice. Our students are a nice, cohesive social group, and pre-COVID had a lot of gatherings, social gatherings of various kinds. We have student organizations on campus that they invite our alumni back to speak, sometimes by Zoom. These days, it has to be always by Zoom, sometimes in person. If it's in person, there's always free pizza involved. Free pizza is a very important part of campus life. And our faculty, many of them receive funding from industry, and our students tend to then find internship opportunities in industry. Some of our students have done internships at national labs, and then they always seem to get hired on as postdocs at the labs where they interned. And sometimes they end up as on the professional staff where they interned. I'm trying to think if there's anything else particularly special. It is well past the application deadline for this year's graduate admissions, and we are actually interviewing the candidates now. But if there were a super candidate that really, really wanted to apply, we haven't given away all our seats yet. Like I said, we're still interviewing candidates. So if you wanted to do a Hail Mary last minute application, certainly in material science, I would make sure it gets attention. I can't promise that in physics because I'm not on that admissions committee. But if there's something that is like liquid crystals and soft matter is my future, I must come to Kent State, we would love to see you. And if you tell me who you are, I will put you in touch with the administrator who handles our applications, and she can make sure to find your application, pull it out of cyberspace, and make sure it gets in front of the eyes of the admissions committee as quickly as possible. Okay. And I'm trying from Chicago, we've had a number of students who came from Loyola, but I don't think we've seen a student from Lewis yet.
Yeah, I think we can make sure that all the students have your contact information in case that they are interested.
Okay, do we have any underclassmen who are not graduating seniors, like rising, freshmen, current freshmen, sophomores, juniors?
Freshmen.
Yeah, there were several. People are starting to filter off.
That's okay. Well, I'll just mention to Jason and Joe, Kent State has an REU funded. We just got the news that our REU it has operated for decades. It did not operate last summer because there was COVID, but also their funding didn't get renewed on the first try. It got renewed on the second try. I don't know if they've made a decision yet about whether summer 2021 is a go. If not this summer, then next summer, which means we have REU opportunities for your underclassmen. And University of Akron got one as well. And so students interested in polymer science would be wise to think about the Akron. Yeah. One of my kids, my own children, participated in the REU at Akron and then went on, he got a bachelor's degree in chemical engineering from Carnegie Mellon, and then he ended up at grad school at University of Texas. So yeah, the REUs both REUs are wonderful.
So could you send that information our way, and we could announce that to our students, students that aren't here right now too.
Thank you. I will check with the PIs to find out if they've made a decision about whether summer 2021 is a go or a no-go. All the conferences I was planning to attend have been switched to virtual. Have you heard anything? I guess everybody's still afraid.
Everything is virtual for us so far.
Every class at Lewis is virtual?
We're hybrid right now.
Right now, yeah.
Yeah, so some classes have an on-ground component, but nobody's full-time on ground.
Okay, well, Kent State has a return to research program that's been in place for many months now. And so people are doing research in the labs, but those are faculty and graduate students and postdocs, not visiting undergraduates living in dormitories. So I do not know what's going to happen with REUs coast to coast.
Yeah, last year it was really, kind of a toss-up. Some went remote and did something virtually, and some just said, we're pushing it to next summer. So
I know, and then those kids were high and dry.
yeah. So we have a number of people who have applied to various REUs, and hopefully they're able to run in some fashion this summer.
I am placing high school students in remote internships only this semester, and so they're doing various kinds of modeling, data mining, computer science, applied math. But yeah, no, I am not going to place a high school student in a lab at this point.
Yeah.
Not yet.
All right, do we have any other questions for our speaker today? Okay, well, I want to thank you for coming to Lewis virtually, of course. Great talk. So interesting to hear about the liquid crystals.
It's a fun field, and it's intermediate. If you think about it, it's interdisciplinary with material science, chemistry, physics, mechanical engineering, chemical engineering, and optics. And don't forget the computer science part. So people working in this field have to be generalists. And one nice thing about physics majors, and I think to some degree also about chemistry majors, is that even though they're trained in one discipline, if they need to learn something else, all you got to do is open a book. It's always new things, And so we can all be, as we move from field to field, we bring what we learn in one field to the next one. And it can actually be very illuminating to work in more than one research field over time.
Yeah, we agree. Lewis, we have a very tight relationship between physics and chemistry, and a lot of interdisciplinary research going on. So, and this fits right in with a lot of the things that we're doing.
Well, so I mean, those students might be really, they might find themselves very much at home.
Yeah.
In the chemistry department. Okay, so the chemistry PhD, it looks like it's pretty generic chemistry PhD in terms of the coursework that's required. And the same for physics, right? All the courses you took as an undergraduate, you put advanced in front of them, advanced mechanics, advanced electromagnetism, and solid state and all those things. But the Liquid Crystal Institute, the material science program is really customizable. There's only 4 required courses. Everything else is an elective. So the students can really pick courses that are tightly connected to their dissertation project. And it's very flexible. So a student whose major is physics or whose major is chemistry could be very happy in the material science program. They don't need a bachelor's degree in material science.
Yeah, thank you for presenting today. And if you get information about the REU, please pass it along, and we'll definitely share your information with all of our undergrads and grads and let them know about opportunities at Kent State.
Well, thank you, Joe, for the invitation, and thank you, Carrie, for hosting. And Jason, it was nice to meet you. And to the students, don't be afraid. I will put my email address in the chat. The chat's on.
Yeah, the chat.
I'll just put rselinge@kent.edu. So feel free to drop me a line if you have questions.
Thanks, Robin. We appreciate it. You have a great
Thank you.
day.
Okay, enjoy the rest of your day. Thanks.
Bye, everybody.
Bye-bye.
Everybody. Thank you.